Welcome everyone to our kind of daily low-level update here. And in yesterday's video we've done just-in-time code generation for MIPS. And of course RISC-V is the latest and greatest in the future, certainly. So here's an icebreaker FPGA board that we previously used for video graphic array-like implementation also. The open source Pico RISC-V, of course, running here, that we also use for our small homebrew microprocessor system. So right now, previous videos, if you're interested in all those details, previous video, MIPS code generation, previous video, getting started with this icebreaker, lattice FPGA, and also Pico RISC-V and stuff. So today only the short update of running our own code here. And for this, of course, I have here at hand the RISC-V instruction set manual, and probably if you're new to this channel, you want to watch the previous videos for MIPS and Pico RISC-V and FPGA stuff. Otherwise, you might miss some details. So as per yesterday's code that is here, and so basically I started copying the MIPS code here and having a JIT RISC-V class here, super minimal as per yesterday. So what are the difference? Actually here, for example, even the JIT32, so RISC-V, so similar. The basic structures of just having the same fixed 32 bits here. And then slightly different here, of course, the difference immediately starts. This is JIT R, I, S and U. These are the formats here of the various, let me just scroll to that, the various formats here of as defined in RISC-V. And here's a register, so that is this R, I, S and U type, similar in concept to yesterday's MIPS. Just this is also what I mean, why is all the stuff not binary compatible and what are the differences? The differences are exactly in this instruction set architecture, that all these numbers here are the fields, the numbers, the structure is somewhat entirely, mostly, depending on, somewhere between 10 and 90% different between all the architectures. Of course, these different types here are used to encode different register to register, immediate, and so on instructions. And I implemented here, so this field here, if you see this from in the instruction machine code, bit 0 to 6, 7 to 11 and so on, all those bit fields here just shifted here together with just one-to-one mapping here in our code to the specification. And then similar to yesterday, we have here move instruction, again the same simplification of not supporting 3 register operands, but just to have one unified JIT here, hopefully for all the architectures, not the perfect performance, but at least hopefully the most readable and simple code. So move, similar to MIPS of yesterday, there you see the similarities. MIPS we might also have used add. Maybe we could actually check. MIPS is just here. So move was, yeah, add with 0 pseudo instruction. Same for RISC-V. Why waste precious instruction encoding space? So move similar. Add, here's a destination, show JIT type R, immediate 0 or something. This is encoding for all of those instructions. Add is 0, 0, that is that part. And then target register, destination register R1 that we supply here dynamically, and source register R2. And then 0 register here, add destination X1 register 1, or doesn't even probably matter the order here anyway. Welcome everyone, how are all of you doing? Nice that you tune in here regularly. If you have any question here live or later, just ask them here in the chat or leave it below the video. So similar to all you see here, this bit pattern actually marks instruction size of the first bits as per the previous live stream RISC-V instruction encoding. Here the first code of the opcode indicate how many the lengths, either compressed 32, so compressed 16 bits a regular 32-bit or 64 128-bit instruction. For those, of course, not in our RV32, but in supercomputer 128 or 64-bit RISC implementations, RISC-V implementations. In this R instruction, in this field here of opcodes, the space opcode is the same, and then this function, this 3-bit function, encodes here at or and, so you see those are all the same, so this is already implemented, or and XOR. I looked this up, you find them here. It takes a little bit, I have to say, this is a little bit less nice to work with this document than many commercial instruction set listings, because you need to scroll it quite a bit. Usually I'm used that if you have the instruction like XOR, it's immediately listed with encoding. Here you need to always search back and forth. Here, for example, XOR, here's this bit pattern of 11001110, so XOR 11001110 exactly here, and then this function 3, the remaining here 001 and 001. You see this specification is exactly how it should be, that the code matches the specification. And again, yes, theoretically sometime soon we can make this also symbolic, but anyway, no operation is also similar encoded. At MIPS this was shift, or at least we used shift. Here they have here an canonical encoding. Again, you could use many variants of not no operation, sub, add, whatever, with all the 0 register, that is always 0, but the standard has an example of NOP that is NOP instruction. The NOP instruction does not change any user visible except something. So this is, they propose here to encode this as add with immediate, and that is what I've done here. So NOP, also known as add with immediate, 0 register, so that is the same bit pattern here, add with immediate, immediate 0 and 0 registers. There we have that. Because right now, so that is, you see how similar that is, and why I want to try this super most minimal just-in-time code generation as most readable example code. Working on that. So to try this out, of course, we have this. I don't have a full like C++ or even operating system firmware on here. So that is why, as a shortcut, I have commented out here. So how do you test this kind of stuff with the first step, also that you learn something at home? Of course, you don't need a full, because on this doesn't have an MMU, memory management unit, so we only have some small firmware running on there. And before we probably soon, why do I do this? Because other people would put BASIC. Of course, I personally not the greatest fan of BASIC, or MicroPython, Pico, Python, or whatever. So to test this also, next step, would it not be amazing to have some Lua-like language just in time compiled here on Pico RISC-V? Certainly, to me at least, it sounds amazing. So before we have this as a first step to test this, because usually when you write something like this, of course it doesn't work at the first try. I commented here in the x86 code path, I commented out JIT x86 and replaced this with RISC-V. Excuse me. And then I have actually run this here, and of course this now, because we are generating RISC-V code in memory, that is this here of our debug printout. So that is a generated hexadecimal printed code that we are generating, but of course running this on x86 here on the AMD Ryzen, previous video, of course segmentation faults here, because certainly jumping here to this instruction is total glibberage to the CISC x86 AMD 64 CPU. However, I copied this here into the code, and that is what you see here. For a quick test, here is a firmware, somewhere at least, should be, I thought I had it open, PicoSoc. So the firmware is here in PicoSoc firmware C. And so what I've done here is I pasted exactly these numbers. You see here hexadecimal to some unsigned in 32 variable here, some array. And then I implemented here in this serial modem protocol thing print JIT. This environment, this firmware environment is so minimal, it doesn't have a printf right now. Probably sometime soon. We will most likely eventually replace the firmware with our own firmware of home computer goodness here with our graphic and sound stuff sometime soon. So print JIT, then we cast here this ugly, totally unreadable C kind of cast. So we cast this JIT variable that is some uint32 to some function pointer. We have some function pointer that we can call, returning int and getting an int argument, and then we call this here int variable I, calling this variable x here, yes, C function pointer, what should I say? It's as unreadable to me maybe than you anyway. Call this here with coffee beat, because why not? Then again this small firmware here of Pico sock, print hex, print here just some formatting stuff. Then we compiled this here, we synthesized this Verilog, also I think the studio lamp, not even best. Synthesized this Verilog here, compiled, cross-compiled this firmware, and then attach here with screen and like memory test and whatnot, pass this memory test. And new in this menu here is J for calling into our sort of also next sometime soon really running this on this, but the outcome would be the same. It's just that I have a super minimal C++ class, just don't have a C++ runtime. Most likely with some little bit of glue code this would work anyway. So the output would be the same if this would be running directly on this Pico RV32, but soon it will be. So calling our buffer here, this indeed works. Outputting here, we called this with coffee beat, the JIT code from yesterday. If you may remember, we JIT here some loading this argument register, loading an immediate 4 into this argument register +1, shifting right. This right shift by this just loaded immediate value 4, moving this over just to test some instructions, moving this over and returning. And it's exactly doing that. We calling it with coffee beat here, and we shift this right 4, exactly the return result. And yes, it did not work on the first try. This is my third try. But anyway, so amazing stuff, in my opinion, making quite some. I made also more progress, but the other progress I made with this FPGA video stuff, actually show you this tomorrow. But that's mostly it for today. We have another way to actually check this with object dump. So am I in the why not? Why is object dump? Command not what? Another way to check this is object dump. So this is the object, the RISC. Of course, I built my cross-compile toolchain with T2, so that is the actually even 64-bit capable RISC-V cross-compile toolchain from our amazing, not one-man, not unsuccessful source distribution, T2. So this is your user source, T2, trunk, RISC-V, and so on, tools, toolchain, tools cross, and so on. So object dump this with capital D for disassembly here on this icebreaker firmware elf thing. And when we take a look at the, darn, I had this previously, now we have this where would, okay, previously I had this as a global variable. This was just not working for some bizarre reason. Let's move this. Previously I had this here, I just moved this for that there. Let's iceproc that and object dump that. That probably should, yeah, so there is that. Also we are flashing this right now. This is another way to check this, because the object dump doesn't know that this is data and not code. So exactly that what we have generated here with our own code here, you see 40 something and so on, B5. If you want to remember that, that is exactly 40 something, B5 and so on. Exactly what our smallest possible code generator actually generated here, and that is load immediate, the argument register 1, immediate 4, shift right logical, the A1 register by the A0 register by A1, and then this move encoded as add argument register hereby with 0. So add A1 with 0, move to 0, or keep storing 0. Anyway, and return. You see exactly how you can follow this flow of data and instruction in your firmware, object dumping, compiling, just-in-time code generation. And actually, now that I show to you, you've seen here object dumping this JIT buffer. So this return instruction also is another special flavor. This is internally actually not return. This also took me some 10 minutes to figure out here. Return is actually also similar to move and no operation, a pseudo instruction that probably should be somewhere written here. Again, took me a while to find, maybe there. So here you see a return, here's some pseudo instructions. So all of those here are pseudo instructions. LA whatsoever, so load address, load global, all of them expand or are implemented internally to something else. It's just providing this pseudo instruction for readability for programmers. You see here knob as add immediate, no operation, and also return is actually, so return from subroutine is actually implemented as jump and I think jump and link register or something with x0. So this is x0, x1 with 0, so because this jump and link register is having an immediate, so that could have been some offset, like you have some pointer with some offset. So this is why the 0 actually is the offset in the encoding. Otherwise register. So yeah, actually, so it's using this register x1 because per the calling convention, x1 is a return address, as you can see here. And there you see how complex, like reduced instruction set computing, but sometimes yet still complex in the implementation details, especially for this internal pseudo instructions that actually a simple return reusing other instruction functionality, because the jump and link register actually can store the computed values. So because of that, it's actually storing the destination register in x0, like throwing this away, register 0 always being 0. So JLR, let's show you that encoding. You see many implemented like that. And again, this is what I mean as, this is also this, in this specification, you always need to scroll a little bit back and forth. So this is the encoding. You see here some offset and destination register. That is why it's using here not storing the destination value that is internally computed, and yeah, base is x1 register and the offset is 0, exactly as promised. That's this overview for RISC-V. I hope you learned something and how all this works internally, that this is not magic, like everyone can get into this, writing compiler, whether working on GCC, LLVM, C-Lang, internally. You can read into all those details. I hope this motivates you to get into this, and also that it's all in the specification. Just read the instruction set architecture here, a document we have previously gone over. If you want to see more details, previous RISC-V video, and otherwise calling convention, all this kind of documents where this stuff is coming from. Sometimes, so next FPGA stuff, I've already made more progress with the video stuff. That is a topic for another video. And so we are making progress on all fronts. So that JIT code was very lightweight C++, but we would not even need to really need C++. I need to see how, if we can use this low-level bare metal on the firmware in C++. Let's see how easy that is to recycle. I hope it is, but anyway, we will see. let's see, how do you feel about hardware synthesis with FPGA Python? Did not look into that. What do you think about something IP from DRAM, PCIe, HDMI you could find in GitHub? Well, yeah, there are many repositories, also open hardware and others, open sock and whatnot, open cores. But yeah, I specifically wanted to get this. Of course, you can reuse other people's cores or RTL, but for me it's also learning all the stuff myself and educating you. So if it's certainly, for a start, you probably want to learn all the details, like I learned here all the hardware, but otherwise, of course, use others people's cores. I actually pushed this stuff already to GitHub, so if you want to take a look, that is on my GitHub page. And bugs me, get a message like 10 minutes in. Sorry to hear this. I try to, in the meantime, I usually pre-schedule this streams at least some 10 minutes ahead of time, but this YouTube notifications, it's a little bit, for some strange reason, I get my own notifications from the More Live channel, in case you want to subscribe to More Live, more promptly and more often than my own notifications for my main channel, whatever is up there with this YouTube stuff. But you can rewind this, and also even if you watch this later in days and years to come and you have questions and answers, always leave them in the comments below. I for sure sometimes read them and reply to them, and certainly people help each other here and amazing stuff. Got into this because of you, brought an Altera after watching your video. That is cool to hear. So this is of course a smaller one. We are running out of logic elements. I need to see, I still need to work on my frame buffer stuff, but video output becoming more amazing. Also in the meantime, this is right now, it is even running my video frame buffer stuff in parallel to the RISC-V, and in the meantime, initially I had some integration issues, but as per the previous video, also I already interfaced this, my VGA stuff with the Pico RISC-V stuff that is interfaced. Today I also made more progress on this, that is for tomorrow's video or something. And yeah, let's see. Running, so this is of course a smaller one, we are a little bit running out of memory and out of logic elements, but anyway, for a start, certainly an amazing board, and let's see what else we are doing with this. So far, the fundamentals, building a computer out of shift registers and so on. For now, the FPGA is on standby. Yeah, cool stuff. Happy that you learned something, and I already inspired some people to get into this. We certainly continue. And the cool thing is, I might not have mentioned this in yesterday's video, so not only are we relatively close, so this is like kind of nearly already running on this, there is just you see, we don't even have printf on this firmware environment. That is why I have, but also inspire you, you do not always need to run this code natively. You've seen I've just commented this out and run this natively here. I hope this also allows you to learn how to creatively test this. You see I've commented this out here, this JIT x86 run JITted RISC-V on x86, because why not? You can do something similar with C-Lang, LLVM or LLVM Clang. They also support JIT'ing or code generation on like cross code generation. Just be creative. You don't, to get this started, you don't need to run this natively. You can pre-process this and copy and paste it just for testing. But sometime soon, the next time, we of course will start to replace the firmware here, so the Pico RISC-V example firmware, with our own stuff like video game or stuff. And then also most likely I will try to combine this with production code. So of course my goal is also to reuse this, make this JIT just-in-time compilation stuff real production ready. Of course right now it's just the most bare minimal example, but just adding enough that it's usable for stuff in our company, maybe single instruction multiple data like image processing stuff and other scripting stuff like Quakes, whatever that was, vQuake, code generation stuff, or Lua or other scripting languages, and keep it stupid simple yet production ready, and use it in our own applications maybe, and also on firmware stuff. I hope you learned something and enjoyed this. That's it for today. Don't forget to share, like, and subscribe, and tune back in for tomorrow or something like that. So one of the next videos, more on the video front here. And yeah, that's it for today. And I hope to see you next time.